Okay, there we are. Good morning, lads and ladies. Welcome back to differential equations. Um, Today we're going to continue where we were last time. You may recall that we left off kind of in the middle of section 4.1, where we were talking about the theory behind general linear differential equations. We talked about a bunch of things. We talked about superposition. We talked about linear differential operators. We came to understand that a general linear order n differential equation can kind of be thought of as really two problems: the corresponding homogeneous equation, where the right-hand side is 0, and then trying to find a different function that gives whatever the right-hand side is when you apply the associated linear operator. Today, we are going to talk a little bit more about linear independence. And I believe I left you guys with a question last time that I'd like to start by answering. But I suppose before we do any of that, I should do the normal hello, good day stuff. So hello, good day. This is MAP2302, which is differential equations. Today is another lecture. And the date is the 15th of July, 2021. Today, we're going to finish section 4.1, which was on general linear ODEs, with a strong emphasis right on the theory. 4.1 is really just kind of trying to help you understand the complexities of general linear ODEs without telling you too much how to solve them. And then, I suspect, we will get into section 4.2, which is on a method called reduction of order. So this is kind of a cute technique. If you have one solution to an order 2 differential equation, this allows you to find another. And for reasons that I'll reveal to you today, order 2 differential equations always have 2 solutions. All right. I don't know how much of what we did yesterday I want to kind of go back over. I don't want to go back over much. Let me just say, recall that a set of functions, a set of, say, n functions, f1, f2, out to fn, is called linearly independent if the equation C1 f1 of x plus C2 f2 of x out to Cn fn of x is identically 0, is only true for C1 equals C2 equals all of these C's are equal to 0. And this is something that happens kind of on an interval, remember, right? So we'd say that these are linearly independent on the interval I if this is identically true for all x on the interval I. Yeah, I guess I should insert this. This. All right. The question I left you with last time So we said that the function f of x equals x and f of x equals the absolute value of x are linearly dependent on the interval 0 to infinity, linearly dependent on the interval negative infinity to 0, linearly independent on the interval negative infinity to infinity. The question I asked you, f1 of x equal x and f2 of x equal to the absolute value of x, linearly independent on the interval, I said to think about negative infinity to 1. Does anybody put any thought into this? Anybody like to give give their thinking on this one? Or?
I was thinking that it would be linearly independent because from negative infinity to 0, the constants would end up being the same, but then from 0 to 1, the constants would have to be opposite for it to be equal to 0. So
that's very good.
Constants that would make that happen.
Yeah, constants have to be constant, right? So that's perfect. That's exactly correct. So what Maxwell said, so again, recall, on negative infinity to 0, f1 and f2 are linearly dependent because on negative infinity to 0, you could take c1 times x plus c2 times absolute value of x. This is, again, because on negative infinity to 0, these are actually equal to c1x plus c2 times negative x. Because if the input to the absolute value function is negative, the absolute value function just multiplies by another negative to make it positive. That's from the definition of the absolute value function. Absolute value is defined piecewise. So you could just take C1 and C2 to both be 1 to make this identically 0. And on any interval containing a positive number, in particular here, I'm going to say on 0, 1, we would have C1x plus C2 absolute value x. That's the same as just C1x plus C2x, which requires C1 equals 1 and C2 equals -1 to be identically 0. That's not entirely true that C1 and C2 just have to be opposites of each other here for this to happen. But in particular, it's a different value of the constants that makes these identically 0 from negative infinity up to 0 than it takes for these constants to give you identically 0 from 0 to 1. So there are no constants. C1, C2, making C1x plus C2 absolute value x identically 0 on negative infinity to 1. So yeah, the answer is that, yeah, they're linearly independent over any interval that contains both positive and negative reals. That's the idea. And I think if you understand this example, then you understand the definition of linear independence for functions pretty well. So this, I would invite anybody who kind of came away from the lecture last time feeling a bit overwhelmed by the definition of linear independence, feeling a little bit uncomfortable with the problems that we solved relating to it, to look at this example in the textbook or look back at the lecture from last time. In the textbook, this is on page 123. They don't go as deep as I did. They just ask, are these two independent from 0 to infinity? And are these two independent from negative infinity to infinity? And that's the whole discussion in the book. But we broke it down further. We looked 0 to infinity, negative infinity to 0, negative infinity to infinity, and then finally negative infinity to 1. And kind of, I think from looking at all of those different cases, it should be clear that these two will be linearly independent on any interval that contains both positive and negative reals. If it just contains positive reals, linearly dependent because they're the same function. If it just contains negative reals, linearly dependent because they're multiples of each other. If it contains both positive and negative reals, then they're not multiples of each other. And for two functions, or for two vectors in general, they'll be linearly dependent if and only if they're constant multiples of each other. If you have more functions, more vectors, then linear dependence and linear independence isn't about being constant multiples. It's about having a linear combination that sums to 0. We'd call it a non-trivial linear combination that sums to 0, because this would be the trivial one. And that can be a little bit harder to sort out. That can be a little bit harder to sort out if you have more than two functions. And that's really the motivation for the tool I'm about to give you. So if you have 3, 4, 5 functions, how do you figure out if they're linearly independent or linearly dependent? Two functions, okay, if they're constant multiples of each other, they're linearly dependent. And sometimes you have to think about the interval in question in order to sort that out, like here. But if you have a shitload of functions, then it can be quite hard. You know, we had the one example with trig functions last time where we were able to sort it out using trig identities and show that sine squared, cos squared, tan squared, secant squared are linearly dependent because we can kind of manipulate them using Pythagorean identities. But showing that a set of 3 or more functions are linearly independent means showing that an equation like this has no solutions except all the c's equal to 0. And that's hard. It's much easier to, you want to say, oh, there is a solution. Here, I found one, right? That's a great way to prove there is a solution. To prove there is no solution, that's a trickier biscuit. So the tool that everybody learns in differential equations for this is called the Wronskian. And I warned you last time that this involves calculating determinants of matrices. So I think as a preliminary to this, let me remind you how to calculate determinants of matrices. And then I will show you the Wronskian. So again, recall. Given a square matrix, A, there exists a real number called the determinant of A. Denoted, there's two kind of common notations for this. Either I like det A, or other people write it with kind of absolute value bars. I'm not a big fan of the absolute value bar notation because it kind of implies that the determinant should always be non-negative, which it isn't. Determinants can be positive, they can be 0, and they can be negative. All 3 are possible. So I like the det notation. Your book uses the absolute value notation. You'll see both in linear algebra textbooks. But yeah, okay. Calculating determinants. Is generally a pain in the ass. If A is a 2 by 2, say A equals the matrix A, B, CD. And I use like big parens for my matrices rather than the square brackets. Either one, again, totally fine. This is just the notation I like. Then I will use the absolute value notation here because that's what your book uses. Then the determinant is the product, the difference of the product of the diagonals. So it's AD minus CB. This times this minus this times this. And when I say that the determinant is a real number, what's actually true is that the determinant is a number from the field that the coefficients or entries in the matrix are taken from. So I'm assuming that the things inside the matrix are real numbers. If these are complex numbers, the determinant can be a complex number. If these are entries from some other field, then the determinant can come from that field. But yeah, generally real numbers. All right, so that's how you take the determinant of a 2 by 2. If A is 3 by 3 or larger, we use, it's called cofactor expansion. About a chosen row or column. So what that means is you're going to pick a row or column, sorry, a row or column to expand about, and then you'll do the following. So for example, if A is BC, DEF, GHI. Forgive me using the letter E and I here. Again, just numbers. Then the determinant of A. At first you have to pick a row or column to expand about. So I'll say expanding about row 1, let's say. Here's what you do. You assign to each of these guys, each entry in the original matrix, you assign a plus or a minus in a checkerboard pattern. So plus, minus, plus, minus, plus, minus, plus, minus, plus, like that, in this alternating fashion. Then, since I want to expand about row 1, I'm going to cover up row 1, cover up, and then cover up one column at a time. So I'll show you what I mean here. And then you'll take the determinant of the little 2 by 2 that's left over. So if I cover up row 1 and column 1, if I cover up row 1 here and column 1 here, then the little matrix that's left over is EFHI. So this is going to be A times the determinant of the little A times the determinant of the little matrix here, EFHI. And the A out front, the little a here, is positive because this guy had a plus. Now I'm going to continue moving along row 1. Next, I get to this B. He has a minus, so I'll write minus B times the determinant of the little matrix I get when I cover up row 1, column 2. So if I cover up row 1 and column 2, that leaves over D, F, G, I. And then moving the rest of the way across row 1, I get to the C. He has a plus, so I write plus C times the determinant of the little 2 by 2 matrix I get by covering up row 1, column 3, which is D, E, G, H. This is called cofactor expansion. The little matrices are called the minors, and the numbers here are called the cofactors. I know it's complicated. In this fashion, we're able to reduce an n by n determinant down to n minus 1 by n minus 1 determinants. So here I wanted to find a 3 by 3 determinant. I was able to reduce that problem down to finding 1, 2, 3, 2 by 2 determinants. So it's a recursive thing. In general, a 4 by 4, you would have to calculate 4 3 by 3 determinants. Each of those 3 by 3s you'd have to do like this. A 5 by 5, you'd have to calculate 5 4 by 4s. Each of those 4 by 4s would require 3 3 by 3s. It's messy. All right, so calculating determinants is a pain in the ass. But this is how we do it. So let me go ahead and finish this up. This guy would be EI minus HF. So this is A times EI minus HF. And then I'd have minus B times DI minus GF. And then plus C times DH minus GE. And that would be my determinant. Some neat facts about determinants. If the rows are, as row vectors, linearly dependent, then the determinant is 0. If the columns, as column vectors, are linearly dependent, then the determinant is 0. And that's kind of where this tool of the Wronskian comes from. Now, just so I have a feel, how many have calculated determinants before? You can give me a thumbs up, react, or anything like that in Zoom.
Is there other names for this, like magnitude or similar? Because this does seem familiar, but I don't recognize the name determinant.
As far as I know, it doesn't have any other names. It's not the same as the magnitude of a vector. Although those are also a pain. Okay, so maybe just 1 or 2 of us, 3.
We use this to find the cross product of vectors.
There is a connection between determinants and cross product. There's something called a triple product that can be used as a sneaky way to calculate determinants. All right, so maybe we should get some practice calculating determinants just for fun. Let's see. Your book doesn't have anything here, but so let's do a few concrete examples. Okay. So here's a 3 by 3, and I want to find the determinant. I could expand about any row or column as long as I follow this kind of cofactor expansion rule. Here, since the way we did this here, we expanded about row 1, so I'm going to expand about row 1 here. A good rule, by the way, whatever row or column has the most zeros is what you want to expand about. Because each one of these zeros will be like a 0 here and a 0 here. So those will be little determinants you don't have to calculate. So I'm going to do this 2 ways. I'm going to do this by expanding about row 1, and I'm going to do this by expanding about column 2, because each of those objects have 2 zeros in them. So about row 1, we see that the determinant of A, here a little checkerboard pattern of signs, plus, minus, plus, minus, plus, minus, plus, minus, plus. This should be 1 times the little determinant I get by covering up row 1, column 1, which is 2107, minus 0 times the little determinant I get by covering up row 1, column 2, which is 0117, plus 0 times the little determinant I get by covering up row 1, column 3, which is 0210. Okay, so that's the cofactor expansion about row 1. And this is easier to do in person, but just to help you kind of see where the little matrices are coming from. For example, here, if I cover up this guy, and my fingers are too fat, I cover up, all right, if I cover up row 3, for example, oh, sorry, column 3 and row 1, you see there the little 0, 2, 1, 0 matrix. That's where this guy down here came from. That's where the minors come from. All right. Now the good news, since I was smart and I expanded about a row that had lots of zeros, I don't need to calculate this because it's getting multiplied by 0. I don't need to calculate this because it's getting multiplied by 0. This is the only thing that matters. So this is 2 times 7 minus 0 times 1. So this is 1 times 2 times 7 minus 0 times 1. And that's 14. So the determinant of this matrix is 14. And just for fun, I'm going to calculate that same determinant again, but this time expanding about column 2. So you can go about any row or any column. You just follow that rule of, you multiply this number by the determinant you get by covering up his row and his column. And then you progress down the row or column, whatever it is that you're expanding about. Just make sure you give the appropriate sign according to that checkerboard pattern. So here it was about row 1. Here it comes about column 2. So det A there, the determinant of A. My first little cofactor is 0, and it would be negative. So I'll say this would be negative 0 times the little determinant I get by covering up this row and this column. So that would be 0, this row, this column would be 0, 1, 1, 7. And then I'm coming down the column. My next guy is plus 2 times the little determinant I get covering up this row and this column. So if I cover up row 2, column 2, that gives me 1, 0, 1, 7. And then finally, I would have minus 0 times the stuff I get by covering up row 3, column 2, right? This is my last cofactor there. So cover up this, and you've got 1, 0, 0, 1. So this would be 0. This would be 0. And I don't even need to calculate them because they're being multiplied by 0. And what I get is just this guy, which is 2 times this determinant, which is 1 times 7 minus 1 times 0, which is 14 again. So,
isn't the second row 1 though? 0 to 1.
the second row in what?
In the matrices.
So in this matrix?
Yeah.
So the second row is this guy. But we're expanding about this column.
Oh, okay.
Yeah, we're going about a column here. So that's one of the cool things is you can go about a row or a column. So here we came down column 2, taking this number times the matrix you get when you cover up this row and this column with the appropriate sign. So when I cover up row 1, column 2, that leaves 0, 1, 1, 7. When I cover up row 2, column 2, that leaves 1, 0, 1, 7 again. Yeah, 1, 0, 1, 7. And then when I cover up row 3, column 2, what's left over is 1, 0, 0, 1. So let me see. I believe. I actually looked at this portion of the site, but yeah. Okay. So if you want to refresh yourself on the algebra of matrices and their determinants, does he explain cofactor expansion? Maybe not. No, it looks like, so here he's just showing you how to expand about row 1. because we won't go into that method here. So it's just giving a formula. That's kind of lame. Let me not send you this. Well, I'll leave this open. I'll share it with you, but I'll find something good for you here and share it. I know the wiki page works, but it's a little bit hard to read.
Should we expect to see matrices larger than like 3 by 3?
Probably not. Probably not. But I can't make promises. Can't make promises. I don't think I would give you something like that on a test. But perhaps as a homework problem, something like that may show up. Yeah, this was actually not a bad explanation. And they've got a few examples. So here they go along row 1. Here, they just like we did, they go along the second column. Then, in this case, their determinant is 0. These formulas are terrifying. Don't worry about those. But here's some other examples. So, oh no, complementary minors. That's even more complicated. I'll find something good beyond this to give you guys. But for now, let's return to what we're doing. So the reason we did that little review is to define something called the Wronskian. So the Wronskian is a determinant of a matrix whose entries are functions and their derivatives. The Wronskian of the functions f1, f2, out to fn is defined as W equals the determinant of row 1 is just the functions. Row 2 is their derivatives, f1 prime, f2 prime, out to fn prime. And then the last row is the n minus first derivative. That's the Wronskian. And here's the nice fact. We'll call it a theorem. It's named after a Polish mathematician named Wronski, Józef Maria on, I'm not sure how to pronounce that name. My Polish is very bad. Mathematician named Wronski. So if you've got some functions and you want to know if they are linearly independent, the set of functions f1, f2, out to fn, these are linearly independent on the interval I if and only if W for those functions is not identically 0 on I. So if W is identically 0 on I, then these are linearly dependent. If W is not identically 0 on I, then these are linearly independent. This actually has a lot of subtlety to it, but I'm trying to couch it in the way that I think is easiest for you to understand. So if you want to check if some functions are linearly independent, one way to do that is to calculate their Wronskian and verify that that Wronskian is not 0 everywhere on the interval. If you can find one number on that interval where the Wronskian is non-zero, then automatically your functions are linearly independent. That's nice. That's a hell of a lot easier than trying to say this equation has no solutions, you know, because it's a single equation with n variables. That can be very hard to do. So for example, the book's example here is gnarly as hell, but we can do it. So where do we have those? Yeah, all right. All right, so for example, check if f1, which is cosine of 2 ln x over x cubed, why not? And f2 sine 2 ln x over x cubed are linearly independent. Now you could argue that this is like cos of some stuff over x cubed and sine of some stuff over x cubed, and that for whatever reason, you know, cosine and sine aren't constant multiples of each other, and try to argue your way there. But it's good practice with the Wronskian. So what do we need? If I'm going to build the Wronskian for these guys, I've got two functions, f1 and f2. That means my Wronskian is really just this, all right? f1, f2 in the first row, f1 prime and f2 prime in the second row. And then we take that determinant. So let's do it. f1, f1 prime. Good practice with our chain rule, quotient rule, all that shit. This is going to be monstrous. I don't know why they're using this example. Well, let's do it though, fuck it. So we take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the square of the bottom. So that's the bottom times the derivative of the top, which is x cubed times negative sine 2 ln x times 2 over x. Is this 2? All minus the top times the derivative of the bottom, cos 2 ln x, top times the derivative of the bottom, which is 3x squared. All of this, sorry, I lost a prime there. All of this divided by x to the 6. I'm going to leave some space over here to try and simplify. f2 prime is going to be pretty similar. Bottom times the derivative of the top here is x cubed times the cos of 2 ln x times 2 over x minus the top times the derivative of the bottom, sine 2 ln x times 3x squared, all over the square of the bottom, which is x to the 6th. And if we can clean this up, we will. So what can we do? Here are our derivatives. The obvious things, I've got an x cubed and a 2 over x in this first factor. So that's 2x squared. So this is negative 2x squared times the sine of 2 ln x. And then minus 3x squared cos 2 ln x. ln x. And that's all over x to the 6. And I'll factor and cancel what I can in the next step. Same sort of thing here. This is going to be between the x cubed and the 2 over x. This will be 2x squared cos 2 ln x minus 3x squared sine 2 ln x that's all over x to the 6. So if we simplify a little further, I can factor an x squared from the top of each of these. We see that f1 primed. If I factor the x squared, in fact, if I factor a negative x squared here, then I will get the x squareds go, and this will become x to the 4 downstairs. I'll leave the negatives. It's going to be 2 sine 2 ln x minus 3 cos 2 ln x over x to the 4 and f2 primed. Same sort of thing. We factor the x squared, cancel the downstairs. I'll get 2 cos ln x minus 3 sine ln x over x to the 4. So that's as much as I can simplify those, at least out of the gate. So now I'll build my Wronski. Why we don't just start with sine and cosine, I don't know. All right, so the Wronskian for this set of functions is the 2x2 determinant, where the first row is f1 and f2. All right, f1 of x, 2 of x, f1 prime of x, 2 prime of x, which here is the determinant cos 2 ln x over x cubed sine 2 ln x over x cubed, and then my derivatives, which are negative 2 sine 2 ln x. I don't even know this is ridiculous. Yeah, I'm gonna have to move this guy way over. Minus 3 cos 2 ln x all over x to the 4. I'm going to recopy this one, so this is sine 2 ln x over x cubed. And then the derivative of f2 prime is 2 cos 2 ln x. Oh, I left off the 2's here, didn't I? 2 ln x, 2 ln x. Minus. I'm making a mistake in my product rule. No, it's okay. Yeah, we're good. Minus 3 sine 2 ln x over x to the 4. I'll do a more tame example after this. All right, so this is a 2x2 determinant. I'm going to multiply this times this minus this times this. And if we're lucky, everything will come out manageable. So that determinant, this times this, is cosine of 2 ln x over x cubed times 3 cos 2 ln x minus 3 sine 2 ln x over x to the 4 minus this times this minus this times this. I'll write the sine 2 ln x over x cubed out front.
Wait, Professor, isn't it 2 cosine 2 ln x, not 3 cosine 2 ln x?
Thank you, thank you. Yes, very good. Yeah, right here, right? I appreciate that. All right. Sine 2 ln x over x cubed times this quantity, which is negative 2 sine 2 ln x minus 3 cos 2 ln x all over x to the 4. And that's our Wronski. So let's see what we get. Looks a little nasty. Oh, and I suppose this is part of the point, right? Okay, so we could try to evaluate this. We could try to evaluate this in general. This is the point. I see now. If you want to know exactly what your Wronskian is, that's great. You can do that. But remember the theorem we have. These are linearly independent as long as the Wronskian is not identically 0 on I. So I don't need to know the Wronskian as a function necessarily. I just need to know if it's always 0 or not always 0. So a valid attempt to kind of prod at this would be to look at the function at one value. If when you plug in x equals 3, pi, e, 7, whatever, you get something non-zero out, you can stop, right? If when you plug in 1, for example, this is not equal to 0, then you know immediately that your functions are linearly independent. Because if you don't get 0 when you plug something in, then that can't be an identically 0 determinant. Is that making sense? Do we want to see the computation anyway? We can do it.
Why not?
I'll be brave. We'll do a little bit more, okay? So the x cubed times x to the 4 from each of these pieces downstairs is x to the 7. I'm going to bring a 1 over x to the 7 out. But I want to be clear here. We could plug in x equals 1 or x equals e. And as long as we don't get 0 out, we can call it a day. Okay. If I distribute cos 2 ln x over this difference, I'll have 2 cos squared 2 ln x minus 3 sine 2 ln x cos 2 ln x minus 3. I'll write the cos first. Now I can factor a negative out here. Bring that out. That will make this plus. And then distribute sine 2 ln x to this. And I'll get 2 sine squared 2 ln x. Plus 3 sine 2 ln x cos 2 ln x, or plus 3 cos 2 ln x sine 2 ln x. All right, some things to observe. This term plus this term is equal to 2, right? If you put those next to each other, factor out a 2, you've got cos squared of something plus sine squared of that same thing. So your Pythagorean identity tells you that sum is 1. So those two add up to 2. Put it in purple so you can see where each piece is coming from. And then the other pieces These are opposites of each other. So -3, some shit, +3, that same shit. Okay, so this is actually 2 over x to the 7, which is certainly not identically 0. In fact, it's never 0, which is a neat observation. And apparently this is the case in general. If you have solutions of a differential equation and you plug them into the Wronskian, you'll either get something which is identically 0 or something which is never 0. And that's the big takeaway here. So in practice,
Wait, Professor,
yeah,
isn't for f f2 prime, wasn't it supposed to be 2 cosine minus 3 sine natural log of x over x to the 4th?
no, there was a little mistake there that I had to correct. So I did correct it, but maybe I did it a little bit too quickly. Where was that? So here, when I copied this down from up here, you see here I've got the 2's. My first row,
Oh,
the 2's,
okay.
I had to insert them. Yeah, I'm sorry. So I noticed it and inserted them quickly. But yeah, these do indeed have the 2's because I just didn't copy them down from this previous line. Okay, so in practice, don't compute the whole Wronskian. When you get to this step, plug in a number. Then take the determinant. Right? You don't want to burn time doing what I just did, especially not on a test. You just want to know, are these functions linearly dependent or linearly independent? And if you plug in a number and you get something other than 0 out for your determinant, boom, you know they're linearly independent. And it is a consequence of our theorem that the Wronskian will either always be 0 or never be 0. So if it's always 0, then you'll detect that by plugging a number in because you'll get 0 out. If it's never 0, you'll detect that by plugging a number in because you get something non-zero out. So much faster to come back here and plug in a number. If I were to plug in x equals 1, then I would have the cosine of 0 over 1, the sine of 0 over 1. This would be the -2 times the sine of 0, -3 times the cos of 0 over 1, 2 times the cos of 0, -3 times the sine of 0 over 1. So this would just be 1, 0, -3, 2. All right, 1, 0, -3, 2. And that's a much easier determinant to calculate than this. You see there's lots of room for algebra mistakes in this process. I made 2 of them that I needed to correct. In practice, plug in a number when you get to this step where you've got your Wronskian written out. If it's 0, LD. If it's non-zero, LI. Okay. A little bit more theory. Just a little bit. These next things are straight up assertions, and I'm just going to make them because proving them is way beyond the scope of this class. Fact. A homogeneous linear ODE has a, of order n, has a linearly independent set of n solution functions. Right. So if you're looking at a homogeneous linear equation, if there are any solutions, in fact, if the coefficient functions are themselves continuous, we know that that guarantees a unique solution to the corresponding IVP. If you're looking at just the ODE under those same circumstances, but without the initial conditions, there will be n solutions and they will be linearly independent. I mean, you can write down other solutions too, but a maximal set of linearly independent solutions will have n functions in it. And that's everything. That's what's called a spanning set. If you've seen any theory from linear algebra, one of the big concepts is finding like a set of vectors that span a vector space. So you want to find a maximal linearly independent set. That's what we're doing here. We call these fundamental solutions. In practice, in terms of the linear algebra, we would say that this is a spanning set for the kernel of the differential operator L. Remember yesterday when we said that you want to scare people, tell them you're finding the kernel of this differential operator? Well, the kernel is a vector space. It's a subspace, the space of all functions. What you're doing when you find these n functions that solve the homogeneous equation is you're finding a set of functions that linear combinations of which fill up the entire kernel, meaning you can get any function such that L of that function is 0 as a combination of these functions. Okay, the existence of these is a theorem in your textbook. Again, the proof of which goes way, way, way beyond the scope of this course. So we're not going to touch it. Now, the general solution to an order n homogeneous linear ODE is, call it y equals c1y1 plus c2y2 plus out to cn where the y1, y2, out to yn are those fundamental solutions. And that's really what I was just saying, that when you try to solve one of these homogeneous linear ODEs, you're looking for these functions y1, y2 out to yn such that, they make the ODE equal to 0. If you take, this is called a linear combination. That's the term, where you multiply each one by their own constant and then add them up. The claim is that when we say general solution, we mean any function that solves that ODE. Any function that solves the ODE can be written as a combination of these. So that's the C1, C2 out to Cn times each one of these. So you find your fundamental solutions, then your general solution, meaning all possible solutions to that equation, come as linear combinations of those fundamental solutions. And these Yn are linearly independent. I should have that here. This is good news. What it means is that when you're solving one of these equations, say an equation of order 2, if you can find 2 linearly independent solutions to the homogeneous equation, you know you found them all. Once you have two linearly independent solutions, the general solution, meaning all possible solutions, is just constant times the first plus constant times the second. That's it. Nothing crazy. There are some examples in your textbook where, okay, here are some of these things, show that they're linearly independent by computing the Wronskian, or, write down the general solution. I'll do one of them. There's 3 of these. I'm not going to do all of them. Let's just do this one, okay? So to give the general solution of y prime prime minus 9y equals 0, knowing that y equals y1 equals e to the 3x, y2 equals e to the negative 3x, both solve the ODE. So what we need to do here, if I want to give the general solution, I need to know whether these are or are not the fundamental solutions. If they are linearly independent, then I know that these are the fundamental solutions, because this ODE, being of order 2, should have 2 fundamental solutions. If they were linearly dependent, then that would mean that I hold on to one and I need to find another. So what we're going to do is compute the Wronskian. So here, off to the side, we say y1 prime is 3e to the 3x, and y2 prime is negative 3e to the negative 3x. So my Wronskian is e to the 3x, e to the negative 3x, 3e to the 3x, negative 3e to the negative 3x. And as long as this is not identically 0, then I can say, yay, these are linearly independent. Therefore, the fundamental solutions, and hence the general solution, is just a linear combination of the 2. So this times this the computation here really isn't bad, so I'll go ahead and do it, minus this times this. So this is e to the 3x times negative 3 times e to the negative 3x. But e to the 3x times e to the negative 3x is 1. So this is just negative 3 minus, and the same thing happens here. E to the 3x times e to the negative 3x is also 1. So this is negative 6, which is definitely not 0. So y1 and y2 are linearly independent. Hence, the general solution to y prime prime minus 9y equals 0 is y equals c1 e to the 3x plus c2 e to the negative 3x. And that's it. Again, the reason this matters is because if you happen to have 2 solutions, but they're not linearly independent, that means you missed one. That means those 2 solutions are somehow like the same, and you need to go back and find another one. So the purpose of the Wronskian or the linear dependence thing is to check if you have 2 linearly independent solutions. If you do, then you know you've found all the fundamental solutions. Or if it's a 3rd order equation, if you've got 3 and they're all linearly independent, you know you found all the fundamental solutions. But if they turn out to not be linearly independent, then you need to throw one away until, throw as many away as you need to in order to get down to a linearly independent set and find others. And that's what the next section is about. It's how to, given one solution, find another linearly independent solution. But before we get there, I've got just a little bit more to say. Questions on the computation here, the theorems, facts, definitions so far? All right. So what about non-homogeneous equations? The general solution here is it's what you get by combining the general solution to the homogeneous equation with the particular solution. So remember the, what do they call it? I think it's the same name, the complementary function. So if capital Y of X equals C1 Y1 plus C2 Y2 out to Cn Yn solves L of Y equals 0, and I'll call it little yp equals, they use a notation for this, they just call it little yp. Little yp solves L of Y, or L applied to Y equals G of X, then the general solution to the non-homogeneous equation is what you get when you add these two up. Plus yp. So, you just take the solutions to the homogeneous equation and add them to the particular solution, the solution that gives you the right-hand side. We haven't talked at all about how to find these particular solutions. This shit's hard, but we'll get there. It's going to be a few sections down the road. Sometimes they call this thing little y sub c. They call it the complementary function. I don't, there's so much notation here. I don't really care what you call it. Just remember to take the solutions to the homogeneous equation, add them to the solutions that yield the right-hand side, and that gives you the full solution, general solution to the non-homogeneous equation. All right, last thing I'm going to say about this stuff, and I know it will really deep into a bunch of language and notation, is that if you have, a non-homogeneous equation, linear equation, everything's linear here, where g of x, the right-hand side, is made up of several pieces. Call it g1 of x plus g2 of x, whatever, to gn of x. Then we can solve individually and superimpose to get yp. All right, so kind of the first useful fact when it comes to solving non-homogeneous equations, when it comes to finding these particular solutions that give us the right-hand side we want, is that you can break the right-hand side down into pieces. So let's say it like this. Just an example. If yp1 equals negative 4x squared solves y prime prime minus 3y prime plus 4y equals negative 16x squared plus 24x minus 8. yp2 equals e to the 2x. Solves same ODE, but with a different right-hand side. Y prime prime minus 3y prime plus 4y equals 2e to the 2x. And yp3 is x e to the x. Solves y prime prime minus 3y prime plus 4y equals 2x e to the x minus e to the x. Then then the sum of these would solve this ODE with the sum of these right-hand sides. Then yp1 plus yp2 plus yp3 solves y prime prime minus 3y prime plus 4y equals negative 16x squared plus 24x minus 8 plus 2e to the 2x plus 2x e to the 2x minus e to the x. That makes sense. Again, it's a shitload of notation, but it's the idea is you can kind of break the right-hand side down into polynomial pieces and exponential, different individual exponential pieces, and find a particular solution for each of them, right? So if your right-hand side, here's G1, like this is G1, this is G2, this is G3. If you have a particular solution for each of the pieces of G, then you can add those up to get a particular solution for the same ODE on the left, but with the sum of those G's on the right. That's all. All right, I think you guys are probably done with 4.1 at this point. I know I'm feeling pretty done with it. Most of it is a little bit intuitive. The thing to keep in mind is that superposition works. A sum of solutions will be a solution to the homogeneous equation. And if you break your right-hand side up into different pieces, you can find a solution for each piece and add those up. Each of those particular solutions will solve the ODE. Will be a particular solution to the ODE. Okay, how do we do this shit? We've got all this goddamn theory. How do we do it? So the first thing I'm going to show you is a method called reduction of order. And this leans really heavily on the concept of linear independence and then kind of yields a nasty looking formula. I'm gonna derive that formula for you, and then I'll do an example. And then I'm going to show you how to solve constant coefficient linear homogeneous ODEs, if there's time. Okay, so this is section 4.2. This is called reduction of order. Sorry, the TV next to me is a little loud. I'm going to turn this down. All right, so here's the idea. Suppose through whatever means you find one solution to a second order differential equation. How do you take that one solution and use it to find another linearly independent solution, giving you the full set, the full solution set? Well, that's the basic idea. So suppose you have one solution, y1, to a second order linear ODE, linear homogeneous ODE. How can we find a second? Second, linearly independent solution. This is something that happens surprisingly often. Sometimes you can like look at a differential equation, a second order differential equation, and a solution just kind of jumps out at you, like sine, cosine, e to the x, something like that. But then you know that the full solution set for a second order equation, second order homogeneous linear ODE, should have two linearly independent functions. If you have the one that you're able to get easily or was given to you, how can you use it to cook up another? Recall. Two functions, y1 and y2 are linearly dependent if they are constant multiples of one another, of each other. Hence, they are linearly independent if they're not constant multiples of each other. Okay. So LI linearly, sorry, LD, let's do that first. Linearly dependent. This would mean y1 is equal to some constant times y2, which I could rewrite as y1 over y2. Yeah, I'm so sorry. It'll be nicer if we write it like this. Y2 is equal to some constant times y1. Same. Which I can rewrite as prime times y1. From the first three here, from this first trio, I can factor out a u, and I get y1 prime prime plus p of x, y1 prime plus q of x, y1. We know that to be 0. And then you have here the other pieces, u prime prime times y1. And then these two I could put together if I wanted as u prime times 2y1 prime p of x times y1. So yeah, plus, I'll put the coefficients out front. This is 2y1 prime plus p of x all times u prime. This piece we know is 0. Because y1 is a solution to the original differential equation. This is the original differential equation with y1 plugged in. So that means that that whole first term goes away, and we get u double prime times y1 plus 2y1 prime plus p of x times u prime. And now this is like the equation we had after our algebra steps in the previous one, where I can now substitute w equals u primed to turn this into w primed y1 plus 2y1 prime plus p of x times w. And so that equal to 0 is a first order linear equation. Now, if you're working through these kind of one at a time on their own merits, then maybe you could solve this like we did by separating variables. But in general, you would need to use integrating factors. Let me jump to the result here. What we would want to do, I'm going to run out of time. Tell you what, let me pick it up here next time. I'm going to save this. We will resume here next time. I'll tell you that the formula we're going to get is that y2 is going to be y1 times the integral of, you're going to hate this, e to the negative integral p of x dx within the big integral, divide by y1 squared of x, or just y1 squared, and then integrate that whole beast dx. So basically, you're going to solve this equation using integrating factors. That's where this piece comes from. And then you're gonna back up and go back through this substitution to find u. That's where the second integral comes from. And then you're going to multiply that by y1. So this is going to be the end result. And I don't mind just giving it to you, but I'll finish the derivation next time. All right. So it's messy. It's messy, but it's fun. And I invite you guys to try and finish it from here. This isn't bad. Treat this as a first order linear equation in W. Divide through by y1. Try to clean things up as much as you can. Calculate your integrating factor, multiply through by the integrating factor. Remember the other side here is 0. Integrate on both sides and you'll get the result. It's not terrible. Alrighty, this is actually everything you need to complete the homework set that's up now, although the homework set isn't going to be due till next Monday because I know you guys have the test, so you don't have the full 3 days to work on the homework set. I didn't want to make it due to you tomorrow. So please definitely knock out the 4.1 by tomorrow. Knock out as much of the 4.2 as you can. We'll finish this derivation tomorrow, and then we're going to move on, and I'm going to start teaching you how to solve constant coefficient homogeneous linear ODEs of arbitrary order. That's where we go next, section 4.3. And then I'll start teaching you how to solve non-homogeneous equations. Well, that's it for now. Hope you guys have a lovely day. Bye.
Professor,
Yes.
By tomorrow, do you mean Monday? Because there's no class tomorrow, right?
Oh, is today Thursday? I thought today was Wednesday. I don't know where my fucking head is. That test really threw me off. Damn. Yeah, okay. Monday then. That's unfortunate. So then you will need this formula, right, to finish up the homework set. And you won't get to see the remainder of this derivation before that homework set is due. I'm so sorry. So I encourage you to finish this. It's not terribly bad. If you want to see it in the book, it is in the book. I do want to finish this derivation for you because the process is, going along with this and trying to understand this is how you learn differential equations. But yeah, this is the formula you need for your homework. I think the homework problems each give you this formula because it's so hard to remember. But yeah, Monday will be our next class where we finish this discussion. All right, take care, guys.